Okay. After much trial and tribulation, handing out papers and quizzes and everything else. All right, so let's chit-chat about the lab. So this lab we're actually going to start today, and we'll finish it up on Tuesday. Okay, so this is like a 3-day lab. So the good news is you really won't have that much homework tonight, just unless you want to like do some calculations on the stuff. So that's the cool thing about labs, that we don't do a whole lot of it. When we do, they're really intense and they're pretty involved. So there's kind of three distinct parts to this lab. So, and they all hinge off of each other. So if we screw up the first part, then the other two parts are going to be train wrecks as well. So the first thing that you want to do is that when you go into the lab, I'm going to have bottles of sodium hydroxide, okay? Your first thing that you have to do is figure out the molarity of the sodium hydroxide, okay? Now, it isn't like you can just like put it underneath a microscope and stare at and count how many sodium ions and how many hydroxide ions there are, okay, which would be cool, don't get me wrong, okay, but we really can't do that. So what we do is we use a compound called potassium hydrophenolphthaleate, which is usually just abbreviated KHP, okay? So KHP is cool in terms of how it reacts to sodium hydroxide. So KHP, which is this big organic compound, and no, I'm not going to expect you to know the formula of it, okay? Don't worry about it. It's just know that it's KHP. So here's the unique thing about KHP. Number one, it's soluble because it has a group 1 ion attached to it. So what you're going to do, and this is why we boiled that water yesterday. So what you're going to do is you're going to take a known amount of KHP. So on what I gave you here on this lab packet, so the first thing you're going to do here is part B, where we're going to figure out the molarity of the KHP. So we already did the first step. We boiled the water. We boiled the water to get rid of the carbon dioxide, because carbon dioxide in water forms carbonic acid. And so if you're trying to find the molarity of a base, you want to make sure that there's no carbonic acid in there that could interfere and react with the sodium hydroxide. So the reason that we boiled it is to make sure there's no carbonic acid. That way, any reaction that occurs is only with the KHP and not with carbonic acid that could also be in the solution. So we did that to basically purge your water of carbonic acid. It's not a lot of carbonic acid in it, but it can be enough to alter our results with the precision that we're going to have. So you've already done step one. Now, you're going to get 3 different samples of KHP, somewhere between 0.4 and 0.6. So maybe have one at 0.4, maybe one about 0.5, maybe one about 0.6, okay? There are 3 different samples. So on the scales that you're going to use, we use very, very, very highly precise scales, and some of you might use these in Chem too. So these scales measure out to 4 decimal places. They go tenths, hundredths, thousandths, 10,000ths. So these are so precise that we have a glass case around them, because otherwise, like if the air conditioner is on and there's air moving out of the vents, it's so sensitive that air movement will alter the reading on the scale. So that's why they're in a glass case. So, and again, it's just something around 0.4. So you're going to take this, it's white powder, pour it out. So your first one might be 0.4172, okay? So what you're going to do, and this is why you have different colors of lab materials. So what you're going to do on this one, this is where you're going to use, on this yellow sheet, the standardization of the sodium hydroxide. So this is what you're going to do first. So you're going to have the mass of your KHP. I'd write down 0.4172, whatever that is, whatever that mass is. The next thing you need to know is the moles of KHP. So the molar mass of KHP, to save you all some time, is 204.2. Okay, so write that down somewhere so that you remember that. So the molar mass of KHP is 204.2. So you're going to have the mass of KHP, you're going to have the moles of KHP. Now, there are times in this experiment when you need to have very precise measurements, and there are times when it's just, whatever. So on this one, notice that it says 3 significant digits, okay? And then what you're going to do is you're going to add sodium hydroxide to it, and you're going to add about 100 milliliters of water, okay? So down here, kind of on the bottom, middle of this page, it says add to each sample about 100 milliliters of distilled water. So in this situation, it's about 100 milliliters. So don't sit there and measure out and get a graduated cylinder and get a dropper bottle and add exactly 100 milliliters. So this is one of the key things you have to be able to know in a lab, is that when is it important to have exact measurements and when is it, it's close enough, okay? So the measurement of my mass of my KHP has to be a very precise measurement. So you're going to have this 0.4172 grams. You're going to put that into a beaker. So you're going to know an exact amount of KHP. Then you're going to take the water that's in an Erlenmeyer flask and it's stoppered. I've got them sitting around. And you're going to add about 100 milliliters, okay? All the water is doing is allowing the KHP to dissolve. I don't need the molarity of the KHP, okay? All I need to know is how many moles of KHP there are. So all the water is doing is allowing the KHP to dissolve. This is why in the lab it says add 100 milliliters. There's no decimal point. It's just add about 100 milliliters. So you could, even on your graduated cylinders, on your beakers, your beaker might have a mark for 100 milliliters. Just add water and just use that to get the 100 milliliters, because it doesn't have to be a precise measurement. All you're allowing all the water is doing is dissolving the KHP. We're not going to use the volume of water in any calculations. That's why it's about 100. Now, if the lab had said you need to add 100.0 milliliters, that's a completely different ballgame. If it had said add 100.0, then you would have to measure out exact volume of 100 milliliters. So that's the difference in how you write up lab styles. If it says add about 100 milliliters, no decimal point, hey, get it close. If it says 100.0, that's a very different indication of the precision that you need. So here's what's going to happen. You're going to have a beaker, or you can use an Erlenmeyer flask. It's a personal preference in terms of how you use the glassware. But the main point being is that you're going to have your KHP is soluble, and you're going to add the 100 milliliters of water. So what's going to happen is that you're going to have this KHP in the water, and it's going to be floating around. Now, to this, you're going to also add phenolphthalein. Phenolphthalein is an indicator. The cool thing about phenolphthalein, and we use this a lot, phenolphthalein turns magenta in a basic solution. So what's going to happen is that you're going to have, I'm assuming that you all have done titrations, okay? At least have a general idea. So you're going to have your little magnetic stirrer, okay? And I'm going to give you a little magnet, and you're going to put the beaker on top of that, your little magnet. That's going to spin, keep everything stirring, right? We're not going to measure the pH in this one, okay? This has nothing to do with pH. We will tomorrow. Tomorrow we'll worry about pH. We're not worrying about pH today. And so you're going to have your little magnet, and it's going to be stirring around, and you're going to look like little scientists. It's going to be cool, right? And you're going to add your phenolphthalein, and it should be clear, okay? Even after you add that phenolphthalein, it should be clear. If it turns magenta, that means you have like some residual base in that beaker, and that's bad. So when you add that phenolphthalein to the solution of KHP, that should be completely clear. So what's going to happen is this. You're going to have a burette. Now let's talk about the burettes. So those are the ones that got a little knob that you turn and you let water flow out of it. And we use very precise burettes that have a capacity of 50 milliliters. So up there at the top, there's going to be your 0 mark, and these burettes are marked off to the nearest tenth. So remember, when you're reading burettes, read from what we call the meniscus, which is the bottom of the curve. So when you get into a lab, especially like this, where it's very technical in terms of your ion analysis, always assume that the people that used the glassware before you were idiots and they left it dirty, okay? So the first thing you want to do is take that burette and rinse it and run a bunch of distilled water through it. Okay, I'm not saying do this for an hour, but at least give it a very good rinse. Open up the valve, let the water run through, okay? Get any residual stuff out of there. Then you actually want to rinse it with the sodium hydroxide solution. And so that way, and the reason that you do that, and you want to do that before you actually start the experiment, because with this small a volume, if you have water, some droplets of water that were in there, that's actually going to dilute your sodium hydroxide solution. So this is why you even want to rinse it with sodium hydroxide, open up that valve, and make sure that water, all the water gets flushed out, so that way when you open up that valve to actually start the experiment, you know it's just sodium hydroxide that's coming out of that burette and not water or dilute sodium hydroxide. So that's why you want to rinse it with sodium hydroxide. So you're going to have your funnels. So what's going to happen is that there's going to be 4 bottles of sodium hydroxide over there, labeled A, B, C, and D, 2 on each side. You want to pull from the same bottle every time. Okay, so that way you're always pulling out of the same one. So I don't care which one, but like A and B are on this side, C and D are on this side. Just make sure that you're always pulling out of the same one. So take your funnel, fill that up to the exact mark of 0. That way you know you're exactly where you're starting. So what you're going to begin to do is that you're going to have this burette. Here's going to be your beaker with a little magnet going around. You have your KHP and your phenolphthalein. So you're going to begin to add sodium hydroxide ions to the beaker that has the KHP in it. So what's going to happen is this reaction right here. And again, you don't need to know this reaction. I'm not going to ask it to actually write the reaction, but you need to know the basic idea. So here you have KHP, and you're going to react that with sodium hydroxide. So what's going to happen is that basically the sodium is going to come in here, and it's going to kick out a hydrogen. So that hydrogen is going to bond with this hydroxide, so you get water. So that's where the water comes from. So that sodium kicks out the hydrogen bonds with the OH, you make water. What's left over is potassium, sodium, and this big complex organic molecule. So it's just like they're switching places. But here's the cool thing about this. This is why we use phenolphthalein. So what's going to happen is that solution is going to remain clear as long as there's KHP to neutralize the sodium hydroxide. So what you're going to see is you add that sodium hydroxide, you're going to see little swirls of purple, but then the purple is going to disappear because of the fact that the sodium hydroxide is reacting with the KHP. So when you get done, what we're going to do and what we're going to look for is when your beaker stays a magenta color, that indicates to you that all the KHP has been used up and now the solution goes basic. So as long as there's KHP to react, the solution remains clear. As soon as you add that last drop, and it's going to look like Peyton's pencil bag. Is that a pencil bag? Okay? When your solution looks like that pencil bag, that's when you know you're done. Okay? That's when you know, okay, we're finished. So what you're going to do is you're going to know the volume of the sodium hydroxide that you add. So this is where the magic happens. So you're going to know, like for example, let's say you have 0.47 or 0.4178 grams of KHP. Okay, you're going to know that number. You know the molar mass of KHP is 204.2 grams per 1 mole of KHP. Okay? Now the other reason we use this, if you go to this reaction, everything is balanced because of the fact that it's a 1-to-1 ratio. So when we do the stoic, there's no 2s, 3s, everything is just has a charge of 1 plus. So that's going to make the math a little bit easier. So I know that for every 1 mole of KHP that reacts, that's going to require 1 mole of sodium hydroxide, because that's what the number means. Oh, everything's in a 1-to-1 ratio. So down here, I want to go, okay, for every 1 mole of KHP, that's going to react with 1 mole of sodium hydroxide. Okay, so if I stop right now, I have moles of sodium hydroxide. But what I'm after is the molarity of my sodium hydroxide. That's the end game. Okay, so molarity is measured in what? What per what? Moles per liter. So at this point, I know how many moles of sodium hydroxide I have. It's cool, I have that number, because I know how many moles of KHP I have. What I don't know is the volume. But where I'm going to get that volume is based upon how much sodium hydroxide I had to add to make that, where that last drop turned into magenta color. So I'm just going to make up a number. Let's say that was 24.52 milliliters. Okay? And if you look on this, on your burette, you're going to know the tenths and you're going to estimate the hundredths. So on any reading that you do with these burettes, we paid a lot of money to get very precise burettes. Use them wisely, okay? So you're always going to know the whole number, estimate the hundredths. And that estimate might be a 0. If it was exactly 24.5, write that as 24.50. So be consistent on how you measure these things. Now, you all know that there's 1,000 milliliters in 1 liter, okay? So down here, I'm going to put 0.0245, or whatever that is, 2452 liters. So that's what's going to go here. So at this point, I'm going to have my molarity. So I'm going to start with my moles or grams of KHP. I'm going to change that into moles of KHP. I'm going to change the moles of KHP into moles of sodium hydroxide, and then I'm going to take the moles of sodium hydroxide divided by the volume of sodium hydroxide. Boom, I have my molarity. Okay? So you're going to do that with 3 different trials. So what I would recommend after each trial, fill this back up to 0. That way you're starting over each time. Okay? You could, use the previous reading and then, drain some more out. So that no more volume that works, since these don't hold very much. I just fill it back up to 0 each time. Okay, that way it just makes the math easier. So what you're going to do is that you're going to have your mass of KHP, moles of KHP. Initial burette reading, I just make that 0 each time. I just fill it back up to there. Final burette reading is going to be however many milliliters you use. Boom, there's your milliliters of sodium hydroxide. Then you're going to calculate 3 different molarities of sodium hydroxide. Now, notice here I tell you, I don't want to have to see all 3 trials, but I want to see one complete set of calculations for trial 1, where you say, this is what I have, here's my mass of KHP, how do I end up with molarity? Okay? Now, the next thing that you want to do eventually is calculate standard deviation. So here's how you calculate standard deviation. And for those of you that have been in stats, okay, so the S with bar over the top of that, that's the shortcut way of saying here's our standard deviation. So X bar is going to be your average. Okay? So when you get done, and you should be able to get all 3 trials done today, you're going to have the average molarity of your sodium hydroxide, which you will be able to go out to 4 decimal places because your mass is out to 4 decimal places. The reading on your volumetric burette is 4 decimal places. So each calculation of your molarity should have 4 decimal places. Evan.
What is the N and what is the trial?
I'll get it. Hold on.
Okay.
So X bar is the average of the 3 to 4 significant digits. The trial is going to be what you got out of each particular trial. So let's say that, I'm just going to make up the numbers. Let's say your average is 0.1052. Let's say that's your average molarity, okay? That's going to stay the same on this calculation. This is going to be like trial 1. So let's say trial 1's molarity was 0.075, okay? So what I'm going to do is I'm going to take this average of 0.105, I'm going to subtract 0.1075 from it, and then I'm going to square that. So that's going to get me 1. Then for the second one, I'm going to take this average minus whatever I got on the second trial, square that. This average minus whatever I got on the third trial, square that. So I'm going to, this sigma means sum. So I'm going to have 3 different values that I'm going to add together, okay? Basically you're going to take the average minus each trial and square it. And you do that 3 times. N minus 1, N is the number of trials. So in this case, this is going to be 3. So you're going to take 3 trials, N minus 1, so I'm going to take 3 minus 1, divide that by 2, and then I'm going to take the square root of everything. And I'm still going to end up in molarity, because this is molarity squared. Then I'm going to take the square root of molarity squared, so I end up back at molarity. So here's the classic way to visualize standard deviation. So let's say you have 2 situations. You have 49, 50, and 51. So standard deviation is a measure of basically the discrepancy between your data points. So you have 49, 50, and 51. Next trial, you have 1, 50, and 99. On both trials, the average is 50. Okay? Same one. This has an average of 50, this has an average of 50. But these numbers here are vastly spread out. So this is going to have a much higher standard deviation than when you have 49, 50, and 51. So your standard deviation is a reflection of how close your data is to each other. Okay? So that's what, so today, here's what you need to get done. You got about 35 minutes. The first trial is going to take the longest. What you don't want to do is blow through it and add too much sodium hydroxide, and then it all turns magenta, and then you don't know exactly where that transpired. So what I would recommend when you first get started, maybe go like in 2 milliliter increments. And you can tell when you get close, because what will happen when you get close, that magenta color will last a little bit longer before it dissolves. That's how you can tell you're getting close to the endpoint. So when you get to that close to that endpoint, you add that last drop of sodium hydroxide, and it turns the color of Peyton's pencil case or the top of her water bottle. Did you buy that as a matching set? They're almost the exact same color. That's why I asked. Okay. Let's go do science.